With the exponential increase in the complexity and the cost of building a chip manufacture line, most chip makers are fabless now. In other words, today's design houses cannot afford the in-house chip fabrication cost, and they have to outsource this fabrication to foundries elsewhere. This gives the foundries access to the details of the chips and the possibility of overbuilding them without the authorization from the design house. Integrated circuit metering or hardware metering is an effective method to defend against this IP infringement. Integrated circuit metering is a set of security protocols that enable the design house to achieve post-fabrication control over their ICs. IC metering techniques are developed to defend against IC overbuilding attacks. As we have mentioned earlier, in the integrated circuit fabrication process, design houses and foundries play asymmetric roles. Design houses have to disclose the details of their IPs and pay the cost to build the mask in order to manufacture their chips. Once the IP is released and the mask is built, the design house will not have any control on them. However, a dishonest foundry can utilize this information and the facilities to reproduce the design with negligible cost. This is known as the IP overbuilding. Can we use digital watermarking techniques to protect the designer's right in this case? The answer is no. Watermark protects the authorship of an intellectual property. In IC overbuilding, the foundry just reproduces more copies of the IP than required and sells the extra copies to make profit. The foundry will not attempt to claim the authorship of the IP. How about digital fingerprint? Fingerprint enables the trace of intellectual properties back to the dishonest IP user who illegally distributed the IP. When the overbuilt ICs carry an fingerprint, the user who has this fingerprint will also become the victim of IC overbuilding. This is because this innocent user will now be considered as the source of these extra copies. How integrated circuit metering or hardware metering solves this problem then? Let's first see how meters work in our daily life. When we talk about the utility meters, like water meter or electricity meter, the meters are installed and maintained by the utility providers to monitor the users. However, in the case of the IC overbuilding, the foundry is the provider of the ICs, and the design house who receive these ICs will be the user. So what we need in our case is actually a reverse metering, where the user wants to monitor the provider. The basic concept behind IC metering is to enable a unique tag to each copy of the IC and make sure that the tag is under the control of the design house, not the foundry. Over the years, many different types of tags have been proposed and used for hardware metering. They can be categorized based on various criteria. First, when the tag can only be used for chip identification, it is called passive metering. The tag in active metering can also do a lot of other functionalities, such as enable the chip, disable the chip, or control the chip. Active metering methods can be further classified as internal controlled or external controlled, based on whether the control is part of the design or not. Intrinsic metering does not need the help from additional hardware components or the modification of the design. However, extrinsic metering methods do. Depending whether the tag interacts with the chip's functionality or not, we have non-functional metering and functional metering. Finally, some tags can be reproduced and some cannot. We call the latter unclonable tags. Serial number is perhaps the most popular and one of the earliest ways for device tagging. A serial number can be physically indented on the device or stored permanently in the memory. This image shows a trust platform module installed on a motherboard. What we see here is it has a couple of serial numbers, for example here and here. These tags are passive, they are extrinsic because they do need additional, like this piece of paper or trying to be physically indented on the device. And they are non-functional because they have nothing to do with the functionality of the chip. And most important, they are reproducible. You can use another tag or piece of paper to cover this, or you can change the numbers here. And it is the fact that these tags can be reproduced make them unsuitable to countermeasure foundry overbuilding. The IC ID tag was proposed around 2007. It is based on the silicon manufacturer variation because these variations occur during the chip fabrication process, and it is generally believed that they are random and uncontrollable. Therefore, IC ID is considered as an unclonable tag and thus can be used for anti-overbuilding. Depending whether the ID requires additional hardware components or not, IC identification or IC ID can be either intrinsic or extrinsic. Let's first see an example of an intrinsic unclonable IC ID based on leakage current. Consider a small sub-circuit with 4 2-input NAND gates, G1, G2, G3, and G4, with 5 input signals, X1, X2, X3, X4, and X5. So here is the leakage of our ideal 2-input NAND gate under different input combinations. However, due to fabrication variation, the leakage on the NAND 2 gate will almost for sure be different from these ideal values. For example, let's consider two ICs both have this structure of 4 2-input NAND gates. Their total leakage and the 4 different input vectors are listed here in this table, and we see a dramatic difference between their leakage values. This leakage-based tag is intrinsic because it does not require any extra hardware. It is also unclonable because it is based on fabrication variations. Will be very hard for any foundries to reproduce these manufacturer variations. Now we show a functional passive tagging method. Recall that in the graph vertex coloring problem, we want to assign each node a color such that any pair of adjacent nodes will receive different colors. In this case, the IP is the solution to the graph coloring problem. Consider this graph and a coloring scheme or an IP. We observe that node H, for example, can also be colored with red or yellow because it has only 2 neighbors and they are both colored with green. And similarly, we observe that F can also receive a color which is brown. And finally, node E can also be colored by green instead of yellow. So therefore, we can create 12 different tags by giving different colors to these 3 nodes, H, E, and F. This is a functional tag because the tag, which are the colors for node H, E, and F, is part of the solution or part of the functionality of the IP. Next, we see active integrated circuit metering methods. Most of the existing active metering methods follow the following steps. First, the design house will modify the design specification, most likely in early design stage, to insert a lock. Then complete the design and ask the foundry to fabricate the design. The foundry will fabricate and then maybe overbuild the chips. Due to manufacturer variations, each chip or each IC will have a unique and unclonable identifier that can be used to authenticate the chip. In the active IC metering scheme, the design house can use this unique ID to actively meter or monitor the IC. For example, by enabling, disabling, locking, or unlocking the ICs. Here is an example of an internal active IC metering approach. The design house introduces additional flip-flops to build what is called a boosted finite state machine. Notice that each added flip-flop will double the number of states in the original finite state machine. Therefore, when we power up the chip and use the path data to select a random power-up state, most likely this state does not belong to any of the original finite state machine. But for the chip to function properly, it has to start from certain initial state. The design house will provide a chip or power-up state specific input sequence to direct the random power-up state to the initial state, such that the chip can work properly. Without this correct input sequence, the IC will be useless. This active IC metering approach uses internal finite state machine to control to control the monitoring of chip. The additional flip-flops make it extrinsic. The use of path ensures that it is unclonable and thus can be used to countermeasure chip overbuilding attack. Finally, we show an external active IC metering approach. In this approach, the design house will add control signals and logical units, such as exclusive OR gate, to non-critical parts of the design. Unless all the control signals receive the proper values, the chip or the fabricated ICs will be locked. The design house will then provide an external key to unlock each of the ICs based on some asymmetric cryptographic primitives, for example, the public key infrastructure. In this case, we see this is an active metering scheme because it does involve the interaction between the design house and each fabricated ICs. It is an external method because the signal comes from external value provided by design house. It is extrinsic because we do introduce additional control signals and logical gates. And finally, it is also unclonable, which means that it can also be used to countermeasure circuit overbuilding.